monolith to modular, navigating the transition. It's an interesting topic. I plan to start with modernization, the need for the modernization, then take modularity as a classical example for the mean to modernization, and then look at a couple of methods by which we can modernize, then look at the tools, methodologies, and the best practices. This can be pretty quick, doesn't take 1 hour unless we have a lot of questions. So first one, the definition of application modernization. It's a process of updating legacy application using various newer computational styles. So the first question is, why do we modernize? Why can't we just develop new applications? Any thoughts on that? Because code is cheaper these days. With AI and other frameworks, you could just develop microservices, modular code, and then start getting your capabilities. So the answer is there are a lot of legacy code probably built over the last 30, 40 years. So the enterprises started picking up code or IT as a main line of the business in early 90s. So we have 30 plus years of legacy code, which contain a lot of business logic, key critical piece of software like treasury software for the bank, and the core security software for the government and the military, so on and so forth. So it's not easy to throw away those code and start developing fresh piece of code. And secondly, integration is a very, very big piece of thing, because most of the time, if you look at the thing that you are doing in your SDLC, you will be solving problems where heterogeneous type of software is not able to talk to each other, or there is a API contract that is broken, or the things are not working properly, performance, diagnostics, security, so on and so forth. So if you look at those problems, if you write new application, you will be reinventing all these problems and start solving everything. Whereas legacy code has the level of maturity that it attained in that particular domain. It's a bank that is running for the last 30 years. All the known problems in the various use cases would have been solved with high level of efficiency. So that's where modernization comes as a key aspect, and most of the platform level companies, organizations who are providing language frameworks and platforms such as Java, Node.js, or other operating systems, middleware, databases, they don't just throw away their pieces. Instead they develop tools and frameworks to modernize your applications, right? We can go through each of the need for the modernization, but before that, let's talk about monolith. What is a monolith? It's very funny to call it a monolith, because all these while we have been developing software, suddenly with the invention of microservices, the previous cool piece of software is badly nicknamed as monolith. It's sad, but that's how the paradigms get shifted, and suddenly we see a lot of bad elements in the monolith. So it's complex, that is bad to read and maintain, very coarse-grained, which is essentially means you can't enhance it, and convoluted, that means very difficult to debug, and intertwined, meaning the modules are very much tied together between each other in the application. It's very difficult to decouple them, and then difficult to migrate. These are the key aspects of a monolith. Now, if you look at each one of these are aligned with the SDLC itself. The first one is the development aspect, and the last one is the migration aspect. So it covers everything. In a sense to say, the monolith is detriment to all aspect of the software development lifecycle. That's what we call it now. All right, the need for modernization. First one, what is driving the modernization is a change in the workload, change in the use cases. So as we progress in time, every enterprise identify new use cases, especially in these times, the use cases are largely around AI. So if you want to leverage AI in your application, definitely either AI should come down or your application need to migrate or modernize, right? You can't have a 30-year-old code connecting with a AI just like a function call. Second one is improved innovation. So because the code is old, you limit by which you can actually innovate in that, because pretty much the skills, the capabilities and the APIs, everything is limited in a legacy code. Mostly they would be running in a life support mode, so there is no scope for innovation. Improved developer experience, large scale code reuse. So Maven, Central, NPM, repository, Docker, registry, all these things contain millions of reusable code, which are all latest and greatest versions. If you're using legacy code, you will not be able to leverage those functionalities, or you won't be able to contribute to that. So if you want to get those cool features, you need to migrate your side of things. Improved deployability, deployment targets, and new platforms like cloud and Kubernetes. You can't, as it is, deploy your old code onto the new cloud environment. You need to have containerization and other REST-based endpoints exposed and things like that to be able to actually be hosted onto such platforms. Improved production efficiency. So this is an interesting topic. If you look at legacy software, most of these things, the enterprise grade capabilities like security, diagnostics, and performance, they are inbuilt into the software itself. Whereas with the new frameworks like such as cloud, these things are coming as part of the platform. You don't need to really write security, diagnostics, and all those things as part of your application. You just focus on the business logic, get your microservices, deploy it onto the platform, and the platform takes care of many of the things. Best example is observability. It's not easy to code observability in your application, right? Observability is another key area, very interesting area. Uh, Previously, when you had a monolith, you have a single log file, a server.log or whatever. Now, if your production goes for a toss, you just need to scroll through the server.log in time sequence and figure out what happened in a specific section. Now, the monolith is split into thousands of microservices. Each one is bothered about one particular use case. And everybody are throwing their own ms1.log, ms3.log sort of things. Looking at the log of one particular microservice is not going to give you any insight. So observability is a byproduct or a negative side effect of microservices in one aspect. But having said that, without being able to observe the entirety of your application, the microservice is going to be really detrimental to any sort of maintenance or production efficiency of your application. Improved maintenance, support, migration, upgradation. So if any of you are working on old legacy code, you would know that none of us know what is sitting there. The original developers who wrote the software is no more working in the company. So if a ticket comes, you need to either look at the prior art around that area, or you need to spend a lot of time reading through the code and understand what's going on. So modernization means you get to the latest and you get the fresh code, and that has better capability in terms of the post-production activities of the SDLC. So again, what I covered largely is various phases of the SDLC itself. So the need is not just one, need is across the board, be it development, readability, support, debugging, maintenance, security, workload, characteristics, use cases, and deployment targets. Across the board, we see the need for modernization. Here is a famous quote from Gartner, which let me read that out. Businesses should adopt a continuous modernization strategy as a more cost effective, lower risk approach that increases time to market and accelerate return on investment. So this essentially means it's not a one time activity. If you modernize today, so any code that we are talking about as cool today is going to be legacy after 5 years or 10 years. So it's not a one time activity, it's continuous upgradation. Now, if you don't do that, what happens is at some point in time, you get into a position where either you need to throw away your $1 billion software, or you need to get extended support from a lot of vendors and struggle in that process. So I can quote my own examples. Java version 24 is the latest one, but how many enterprise customers are there on 24? Very little or zero. 21, 17, maybe little more, but the majority of the customers, or at least a large chunk of customers, are on Java 8. Yeah, they're unable to move. Of course, there is an obvious reason, the modularity, right? So they try to calculate the cost for migration versus the cost for purchasing extended support. The purchasing extended support happened to be cheaper than migrating this code from Java 8 to 11. And of course, enterprise look at the business needs and the cost effectiveness, and they still stay at Java 8 and ask vendors to support that for years to come. So we are asked to support Java 8 initially till 2025, then 2030, then 2040. Now there are clients who are asking us, can we support Java 8 forever? Well, that's the sweet spot they found it. They are happy with the code, they're happy with the efficiency and the performance, everything. Why move? Just for the sake of modularity. So the lessons from that is, if you don't modernize, if you don't make updates to your software time to time, you get stuck. You get stuck without being able to innovate, without being able to leverage the cool features of the modern use cases and the modern business. Any questions or comments at this point? All right. Sorry. Yes, absolutely. Modernization is not easy. So that's my topic. We have 4 different modernization types identified by working with the various clients sitting at different levels of maturity, different levels of investment that they can offer, different levels of complexity with their code base, mission criticality of the use case they are running on, so on and so forth. So the first one is re-architecture. Re-architecture is to come up with new architectures. Architectures are nothing but components and their interrelations. So define modern architectures such as whatever the legacy service-oriented architecture with the reactive architecture, whatever. Make only the components different, their interrelations and connectivity different and modernized, but the majority of the business logic still is rested with the code. So the code is not changing, only the interconnectivity, the overall architecture becomes modern. The second one is refactor. Refactoring is again the lowest level of code is not changing, but their interactions, API level interactions change. The tightly coupled code becomes loosely connected, so that you will have component based concept on the code, and you can shuttle between, or you can swap the dependencies with relative ease. So that is one aspect of the modernization. This is in fact what I'm going to specialize in the next slides. retarget is also known as lift and shift. We change the target platform or the deployment targets on-prem to cloud or that sort of a thing. Non-containerized to containerized. Not necessarily a lot of code changes is required, but again, the endpoints need to be defined properly. And rewrite. That's the answer to your question. Rewrite is basically keep the old code there, look at that, and start writing the new code in the new way, which is absolutely taking us time and money a lot. So I'll focus on the second one, which is refactor. But this is again my our understanding about talking to the clients. If you have other patterns of modernization strategies, please feel free to comment on that. So what it takes to modernize through refactoring, it involves restructuring and breaking down the monolith application into a collection of small, loosely connected, loosely coupled, self-contained microservices. Does this require code changes? Yes, it requires, but not necessarily the whole code needs to be changed. The way the modules are interacting with the externals need to be redefined. So the key thing with refactoring is the modularity, which Java 11 introduced as a platform level capability. It's what is a module? Module is a collection of packages, resources, and metadata. So I don't think I need to go deep into that. Another type of modularity or modules come by way of OSGi. OSGi stands for Open Standard Gateway Interface, which largely is consumed by Eclipse. So the concept remains the same. Concept came much before the JPMS. JPMS came in Java 11, but Eclipse adopted the modularity probably in 2001 or 2002. We'll talk more on that later. So the three types of modularity I want to introduce. One is the Java platform modular system. Second one is OSGi with PDE. PDE stands for plugin development environment. And BND. I don't think BND has an expansion, but both of those confine to the OSGi specification, conform to the OSGi specification. So I have this table here, which is basically comparing the scope of JPMS versus OSGi. JPMS is a standard across Java, and it's coarse-grained. It operates at the level of entire Java modules, and it uses module-info.java, limited dynamic capabilities. So that means the modularity capabilities or the things that you're exposing, the things that you are importing, everything need to be statically defined, and there is no dynamism inbuilt. And in terms of adoption, that's now getting widely adopted because based on the business needs that we talked about earlier, people start understanding the criticality of the modularity aspect. So the new code that is getting developed is purely based on the modular system. One another aspect of the modular system which we experience in the JDK itself, that probably when we migrated to cloud is when we realize that Java SE itself has thousands of classes. Java util, Java lang, java.awt, java x.swing, so on and so forth. Now in cloud, you don't need to have AWT and swing. I mean, it as a simple example. Nobody can run GUI applications hosted in the cloud. So, but with the tight coupling in the JRE, we have no way to take it out. But with modern Java, with the modern JVMs, using modularity, we are able to reduce the footprint of the JRE itself by stripping off the unwanted elements from the JDK itself. So if you are saying, I'm going to run this Java application in a container, then you don't use the regular heavyweight JDK. You go to the container hub and choose one that is suited for you, which will not have the graphics packages and other things. That will be only limited to the specific platform capabilities, UBI packages and Slim packages, Alpine Linux. So they will have only the very core capability of the OS. Then Java, for that, will have only the one that is required for running in the container. So that way you reduce the memory footprint as well. But why we reduce the memory footprint? In cloud, memory is charged. So the key benefit of OSGi based modularity is that it, apart from decoupling the modules, it also provides dynamism. What do you mean by dynamism? You could actually change the modules at runtime as long as the API contract between the producer and the consumer is adhered to. So if you have a version 100 of your consumer running in an Eclipse or in a production, and then you got an upgraded version, usually we shut down the server and apply the patch and restart the server. But with the OSGi kind of capabilities, OSGi kind of modularities, you could actually decouple the consumed module and reload the plugin which has the latest version, and then start connecting it. So that's what I mean by dynamism. So now the difference between OSGi and JPMS is understood. Where do we use? So where do we use JPMS? Where do we use OSGi? Apps aiming for efficiency, security, and minimal size, no frequent changes in the dependent modules, we go for JPMS. Components developed by same team. This is very, very important, because if you're developing a module and if your team is developing module B, then you know what is changing in module B and you can make changes to module A. Whereas if module A is developed by your team, module B is developed by some other client or a vendor, you don't have a informed decision about what are the APIs that are changed. So in that case, it is better to go for OSGi. That's because you can only look at the specification of the consume module and then make the changes. As long as the API contract is made, then the promise by the consuming module is that nothing is going to break. If there is a breakage, they will up the major version. So by looking at the major version, you can say nothing is going to make. I can just download the new software and use it just as it is. Another metrics, team composition versus modularity times. All application developed by the same team, JPMS, developed by multiple, I think it's a repetition. Yeah. Okay, this is between PDE and BND. So I told about the Eclipse OSGi types. What is the difference between PDE and BND? In PDE, when there is a change in the source code, you go ahead and make changes into the manifest, which is the modular metadata. In Java, you have module info.java, which is defining the contract between the producer and the consumer. Whereas in Eclipse, you have something called manifest.mf, which is defining the modularity, which is defining the contract between the consuming bundle and the producing bundle. So if you make changes in the source code, say for example, you change the signature of the API, which is a breaking change, you go ahead and make changes in the manifest.mf by bumping the major version. In BND, you don't need to do that. The moment you make changes in your source code based on what contract is being violated what contract is being preserved, the manifest bundle is automatically adjusted by the BND tooling system. So it's as good as in JPMS. You have modulinfo.java, you keep adding new capabilities, APIs, you are removing existing capabilities, etc. You are not touching the modulinfo.java. Everything is taken care automatically. That's the kind of effect if you use BND. Is it confusing, or it's a tooling on top of the modular system? So in summary, we have these capabilities between PDE and BND. One is PDE doesn't use bytecode analysis because it's manual. It look at the changes that you made in the source code and go and make manual changes in the manifest. Whereas in case of BND, this is automatic. How does automated process happen? By looking at the bytecode that is generated by the classes and see how the interdependency between the module got changed, and based on that, the module system is adjusted. So that's happening under the cover. So that's one of the best practice, especially when you're writing complex code with a lot of interdependencies. Many times these dependencies get broken or alerted by the compiler. Sometimes the compiler doesn't uh, take note of that, and it breaks at the production. So if you have this tooling in place, the contract with the tooling is that sort of a breakage doesn't happen at the production, because the API consumption between the modules are very well monitored by the tooling system. Okay, this is a series of questions. Now, given that this is how the modularity is inbuilt into the application development lifecycle, the question is, which factors are critical when it comes to the modularity? Deployment target versus modularity types. Do we need to worry about the deployment target, and based on that pick choose a modularity type between JPMS or PDE or BND? Is it based on where you're going to host your software? It's not. It doesn't depend on where you're going to host your software. Application architecture versus modularity types. Whether the modularity type depend on the specific architecture. For example,
Suppose database
yeah,
application
mhm,
that
that will depend on whether you should go for modularity or not. It should be the code should be developed modular or not. The question is which modularity type to pick from, JPMS or PDE or BND. Will it depend on the architecture? It doesn't. Anybody says it does? It doesn't. The workload type, like if it's a computation intensive versus IO intensive versus distributed database systems versus backend versus front end, it doesn't. Obviously, then the question is what it depends on. Java version types. Obviously, if it is below 11, then there is no inbuilt modularity, so you can't use JPMS, right? But other than that, between 11 and 24, is there any selection criteria? No. You can go for JPMS or BND or PND based on some other choice. Operating system, absolutely no. It's not connected at all. So the question is what it depends on. Okay, I thought I wrote the answer here. I did not. It depends on the team composition, right? If you're writing everything, you could go for JPMs because you know the consumer, you know the producer, you know when you're making change here, you can adjust the change here and vice versa. Whereas if you're working with a number of third-party vendors or your application is really complex with a lot of dependencies, then uh, PDE and BND types is better because they are bound by a spec, they are bound by the API contract. Now the next question is between PDE and BND, which one will you, sorry, how do you choose the selection? I think I may have an answer for that. No, I don't have. So the answer is it's your choice. It's a trade-off. You want finest level of control on the dependencies, you go for PDE because you know I made this change in the API. So I want to control that. I want to be conscious about that and I make the change in the manifest bundle. Whereas I don't care about such things. I want to delegate it to the tool and I focus on the developer productivity. I focus more on dynamism. I go for BND. The BND under the cover takes care of the dependency management, right? So here are some of the best practices. Apply top-down approach from application architecture to define the modules. There are tools available for you to look at how this can be broken down into various modules. But I mean, I'm assuming that there is no tool available. You are given with a legacy application and somebody is asking you to convert into a modern architecture, then this is how you look at identify the patterns, identify the abstractions, and see which are things that can be graduated into modules. It can be based on runtime characteristics, it can be based on code readability, it can be based on code reusability. We had some bad examples from the field purely based on how the classes are composed, purely based on naming conventions, purely based on how the call hierarchy is happening. People started developing modules. But then what happened is some modules became super performance bottleneck because all the traffic is going through that, and you had 99 other modules which are not used at all in the production. So it's not just a function of how the legacy code is maintained or laid out. It's a function of the runtime characteristics of the application by which you should be breaking down into modules. These are the tools that I was talking about. Mono to Micro provides a comprehensive understanding about how your application is laid out in its binary form. You don't need to feed the source. You can feed the jar files and it will come up with a comprehensive analysis and say, these are the things that you can graduate to modules. These are the things that you can make it into microservices, so on and so forth. Transformation Advisor is one step ahead of Mono to Micro, which uh, incorporate some AI elements into that and also try to extrapolate into the runtime characteristics and provides recommendations about how this can be modularized. Azure Migrate is another one. I haven't tried that particular thing. Google CMAP, VMware, Tanzu, and OpenText App Mode. So if you remember my sentence in the first slide, I'm talking about a lot of legacy code out there which cannot be thrown away for various reasons. And the industry has recognized that as a problem. And here is the proof that most of the companies, most of the platform level companies have come up with tooling to help the clients to migrate or modernize.
Okay.
All these tools could be like 5 years old, maybe maximum. So that shows when this problem has started hitting us.
Yeah, moving forward there, diving in.
Uh-huh. I don't know. I haven't used it. Okay.
That's the subset what that's what may fit months in fact. That is correct.
Okay.
Okay. What the
Okay. You mean it's a question if the dependency is spread across multiple. Yeah. So I don't think it is in the purview of this tool to actually go look across the board, because anyway those are network endpoints. Are they across the network endpoints? So that is a classical breaking point, right? You don't need to have a module that is partly sitting in one system and partly sitting in another system. So if you see such a network call or a endpoint call, definitely that's a module boundary. Yeah. I'm thinking that's the way these tools used to operate.
the immediate dependent type you
Okay. Yeah. Yeah. Largely, I think the majority of the complexity these tools are involving with would be looking at the call stack and see where we can break it based on various predicates and various filters. Now, that makes it pretty complex because of the abstract classes and interfaces. You don't know which,
Yeah.
to know the exact call sequences, you need to collect samples at runtime, because these interfaces are resolved at runtime based on which is the receiver object, then the call stack, call sequence change, right? So that's one challenge. The static analysis is not sufficient, and even if at runtime, if you collect all these real call paths, still the performance characteristics which I told earlier also would apply. It's not just the code, but also how the traffic is going is also a major consideration. Some of the methodologies which I told about: convert hot components into microservices and build DevOps into dynamic components, integrate components with observability. So, observability is a key aspect. So, make sure whenever you uh, define new modules, you also need to have a best practice in place that if something goes for a toss in this particular module, how do you capture it? What is mechanism in place to actually figure out what went wrong? So you need to have inbuilt observability as part of the modularity exercise. Previously, that was not the case, but now this is one of the best practice that we are looking at. Choose the right architecture, choose the right level of abstraction, right data resources, sponsor users, automate as much as possible, keep up with the latest technologies, keep future enhancement in the view. So sponsor users is something very interesting which we found. Like, rather than developing everything from based on a perceived notion of requirements, you actually, this is largely related to products. Of course, if you're working for a client, developing a solution for the client is the sponsor user. But if you're developing a product, then you don't have a client. You may have a use case. You are thinking that this product will be used by these clients, but who did the validation? So have a sponsor user, sponsor client early in the cycle, and that way you can understand the characteristics, business needs, execution, environment, platform, supported platform version, so on and so forth. And based on that, you could take calculated decisions about how do you plan your modernization strategy. And again, it's not a just one-time thing. So thinking that modernization is a continuous activity, having sponsor users in the pipeline is definitely a great idea that will help a lot of development cost and effort for your organization. Yeah.
into the body vision architect of that
Hmm.
but process data about
So the previous slide I said the modularity type selection doesn't depend on the architecture. The modularity itself depends on the architecture. Let me explain once again. uh, you want to define a module, let it have 10 classes. And will 10 classes qualify for a module? Not necessarily. What qualifies for a module? It should have a well-defined input, and it should have a well-defined capability, should have a well-defined output, like a REST API backend, right? It's a classical or a DB proxy. It receives a request, gets a piece of data from the DB, and do some processing, transformations, and give to you. So that qualifies for a first-class module. That modularity, that modular concept depends on the entirety of the application's architecture. The, the previous slide, I was talking about when you select how to modularize through JPMS, Java, SC's modularity technique, or Eclipse based OSGi modularity type technique, do you need to look at the architecture? Based on that, will you select one of these? Answer is no. The selection of modularity type depends on how are you developing? Is the whole team in one floor or one company or one organization sort of a thing? If yes, JPMS is the best one. Thanks. That is pretty much it is. These are some of the links from where I captured this slide. And just to reiterate, modularity is absolutely essential for long-term sustenance of the code base, especially with a lot of changes happening in the modern way we develop things, the modern business requirements, the AI workloads, etc. If you have a coarse-grained application which cannot be connected or which cannot connect with anything else, the code becomes obsolete. And based on the investment your organization can have on that, the code can be thrown away, or you may be asked to actually circumvent that by putting a lot of effort. So inbuilt modularity, meaning these kinds of effort becomes very, very, very minimal. So that's the key takeaway from this slide. Thank you so much.